The Hall effect. Now that the Hall effect is well established, it's well understood that you can use the Hall effect for a number of other measurements, and that's what the Hall effect tends to be used for. But back in the day, the Hall effect was the de facto way you could prove definitively that the charge carriers in the wire were negatively charged. Think she's coming back?
I don't know, she had her back.
I just decided sign out was the better option. Is that coming up? There we go. All right. So here's how you set up the Hall effect. First, you do need to have an applied EMF. And we assume some simple wires, but at some point in the circle, you replace the simple wires for a very wide and relatively thin strip of conductive material. Something where the charge carriers moving through the material have a kind of two-dimensional motion, or the possibility of two-dimensional motion. So you want the strip to be very thin compared to how wide and long it is. The resistance I'm putting here is simply a holdover resistor. You don't have to have a resistor here so much as this represents the resistance of the system, and we're going to have an EMF or a battery here, a voltage source. The idea is pretty simple. Let's assume for the time being that we're dealing with conventional current. We know that conventional current would be this direction based on the potential difference of our battery. So if our charge carriers are positively charged particles, then a positively charged particle entering the strip would have a velocity, a drift velocity in this direction. So if we were to surround this, the strip, only the strip, with a magnetic field into the board, then the individual charged particle will experience a force while in the region of space where the strip is. Now you should determine the direction of that force using the right-hand rule. Thank you. And verify that the force in that particle is to the right. Right? Something like that. Now, bear with me. The drift velocity of particle is downward. It experiences a force to the right. That particle is going to begin to drift this way. And so as the charged particles move through the wire, we get an increase of charge that is positive on the right side of this strip, revealing available electrons on the left side of this strip, because our charge carrier is a positively charged particle. This will create an electric field inside the region of space that contains the strip in a magnetic field. So basically, particles are going to build up on one side until the electric force from that electric field is balanced by the magnetic force. Something like this. We've talked about this balance before. It'll be like a selector, except this is because the particles are moving through the wire. Kind of a Q drift velocity B equals QE. Now on the surface, you might say, well, the charge cancels out here. So how could we use that in any meaningful way to measure whether the charge carrier is positive or negative? Well, consider what would happen if we repeat this thought experiment, but in our new thought experiment, we set up the exact same laboratory arrangement, except this time we consider what would have to happen in the strip if our charge carriers were negative. So same strip of material, same potential difference as our source, same resistance in our materials. But this time, although we use the same magnetic field, if our particles were negative, then even though the current is said to be going this way, the charge carriers would be negative charges moving in the opposite direction. I mean, I said we don't know the difference, but if they were negative, then they would enter here with a drift velocity in this direction, but they would be negative. Using the right-hand rule, they would experience a force as well, except their force would be to the right. That would be the magnetic force on those particles, right? Because they're negative charges, they experience a force that is in the opposite direction of what a positive charge would experience. Right-hand rule points to the left, but they're going to experience a force to the right, which means those charged particles will be diverted to the right. But they're negative. So we get a buildup of negative charges on the right-hand side, revealing positive charges on the left side, and an electric field that would be in that direction. Mr. Shelton, what does that mean? Well, it means quite simply that across here, if we connect a voltmeter from either side of this strip, if the voltage is positive, we know the electric field is in one direction. The voltage is negative, we know the electric field is in the other direction. Negative charged particles would have a voltage in the opposite direction produced by positively moving charged particles. The Hall effect is a means of figuring out what's actually moving in the wire. Because although you'll get the same voltage across the strip, you get positive if it's positive moving charged particles, or negative if it's negative moving charged particles. It's a simple experiment. Now, there's more to this experiment, but that's the start. And it's relatively straightforward. Now, the Hall effect, as a laboratory goes, has been difficult for me to set up for a number of reasons. And I'll go through a few of them. You have to have a uniform magnetic field. And you have to have it has to be long enough to extend enough where you can have a long strip of some kind of metal. If we look at the nature of what you have to do to get that, you also have to have a very sensitive device for measuring voltage. This is going to be huge amounts of voltage. Remember, the drift velocity is relatively small. And because it's small, we're not going to get a huge buildup of charges in one direction or the other. And if you try to make the drift velocity faster by getting a higher current, you just burn up the wire. So there's limits to what you can actually do in the classroom unless you have some pretty sensitive materials. So I'll try to set it up again. I've been unsuccessful every year, but maybe this year things will be different. I don't have high expectations, but I have expectations. There are a few other things about the Hall effect that are worth exploring, but I think the basics of the Hall effect is what I want you to know, and those are the basics. So there are a few other things we should add to this. First, you can work in the electric potential as opposed to the electric field by knowing the width of this strip. By measuring the width of the strip, you can put this in terms of the electric potential. That way you know what your expected electric potential should be. But this is in terms of the drift velocity, which we don't really know. But we have an expression for the drift velocity in terms of the current in the wire. You should have that in your notes from just a couple weeks ago. Could you find it? To make sure we're all keeping nice, accurate notes. Something like current density equaled current over area equals, and probably some, something with an N in it, a drift velocity, E. Those are probably some things in this formula. Can you dig it out and find it? Yes, sir.
Is it I is equal to N capital A capital B E?
I is equal to
N A B E.
something like that.
They didn't have a B, but I guess.
Well, I have the A on the other side, so this is what I would probably have written down. Current density equaled N times VD times E. Remember, this is the number of charge carriers, or the charge carrier density in the wire. This is the charge per charge carrier. This was the drift velocity. This was the definition of current density. So we could solve this for the drift velocity instead. And we get I over NAE. Now, these are easy things to measure. This is the cross-sectional area of this strip. This is the charge on the electron or the proton. And this is the charge carrier density. Now, that's harder to measure. But if we do some substitution, we'll get I times B over NAE equals V over D. Now, this is what I want you to pay attention to. A is the cross-sectional density. A is the cross-sectional area of this strip here. It's, if you to have some extension, it would be this area of this side. That's what A represents, the cross-sectional area. D represents how wide it is. That's this. So A over D would be how thick the strip is. Something you could measure with a pair of calipers. It'd be in meters. I'm saying that might be something easy to measure. If we recognize that we have that here, meaning we've got the A and the D here, we could solve this for any number of things in this equation. So, for example, I'm going to put T for thickness. The Hall effect is actually used to measure something else. And I'm not making that particularly clear, but let me point it out now. You could solve this for N. Everything else here is very easy to measure. Once you accept that the Hall effect works, it's actually used to measure the charge carrier density of different materials. That's what it's actually really good for. Because you can put any material in there, and by getting simple measurements, the Hall voltage, that's the voltage across the strip, the applied magnetic field, the current in the wire from a current meter, the thickness of the strip that you're using, and the accepted value for the charge on the electron. All very easy things to measure or know. You can figure out what the charge carrier density is of your material. So although the Hall effect was used to determine that the charge carriers in the wire were positive or negative, today it's used to figure out charge carrier density for materials. It's a relatively simple lab to set up. For us, we could do that. We could grab any group of metals that we have around the room, make a strip. So aluminum foil works best, but we could use any kind of strip and use it to measure what the charge carrier density is for the various different materials that we have. All right. So rewriting this as I dB over NAE equals V. A over D is thickness, so D over A has to be the inverse of thickness, or 1 over the thickness.
Why is it over the thickness?
What's that?
Why is it over the thickness?
Well, A is cross-sectional area, so if I look at this side would be the thickness, this side would be D, so A equals D times T, like a rectangle, length times width. Is that okay?
Yeah.
I'm sorry, I did kind of blow right past that super fast.
No,
You're welcome. I mean, I tried to draw a pretty crappy picture, though.
that's right.
All right. I know. My drawing could be better. Okay, Oliver?
I'm kind of confused about which V is which in that formula. Is that drift velocity
or is that electric potential?
Anything with a D on it is drift velocity. Anything without a D on it is electric potential. I never wrote velocity here without putting the D next to it to try and stave off that problem, because I know that's an issue. Is that okay?
Yeah, I'm just trying to figure out where everything's coming from, but I can just see that on the end.
Well, this is the drift velocity.
Yeah.
I substituted it in here. And that got rid of the drift velocity in that relationship, but kept the potential across the strip.
Oh.
Is that okay?
Yeah.
Yes, sir?
What does the E stand for?
Charge on the electron or the charge on the proton?
Will that always be the same?
Well, yeah. We believe it's like from first semester, we believe that's an accepted value. At the time, and let me be, at least just take a little historical view, Ne was considered the charge density of your material. It wasn't just the number of charges in your material or the available charges in your material. It included how much charge there was, because they didn't actually know the charge on the electron at the time. So this combined to be a single value they called the charge density. Now, they knew it had to be made up of the charge per charge carrier and how many charge carriers there were in your material. But they didn't know the charge in the electron at the time. So you guys do know the name of the experiment that determined the charge in the electron, right?